Hello again. I'm Graham Kilshaw from Lectrix, and if you're just joining us, I'd like to welcome you to the Virtual Summit, Technology and Solutions for Next-Gen Communication Systems. Let's get to our second presentation of today's event, and welcome once again Ronan Cohen. Ronan is the Senior Product Manager of Precision Timing and RF Devices at CTS, and he's just about to get started with this next session, 5G mmWave systems and noise consideration. So whenever you're ready, over to you, Ronan.
Hello, and thank you for joining CTS's Precision Timing presentation addressing 5G mmWave new radio systems and noise consideration. I'm Ronan Cohen, a Senior Product Manager at CTS Electronic Components, responsible for precision timing and RF devices. In our discussion today, we will address a few topics. We'll start with a quick introduction to CTS's frequency control product portfolio. We'll talk about 5G system noise requirements, some of the challenges and constraints. We'll talk also about how the reference source, the frequency reference source, affects the noise level when it comes to time domain and frequency domains. We'll talk about EVM, the error vector magnitude, and the proportional contribution of the oscillator noise. And then I have prepared a few examples and cases that relates to phase noise versus EVM and see how phase noise really affects EVM. And then when we look at some of the solutions, we'll look into low noise jitter attenuators or frequency synthesizers that allow to reduce some of the noise level in the systems, whether clean jitter or allow very clean multiplication. And with that also have a wider introduction to CTS's 5G product family, and we'll wrap it up with a quick conclusion. CTS has been a designer and manufacturer of frequency control products for over 50 years. As technology evolved, higher frequency, tight stability, and definitely low noise has been high in demand. And with that, we have focused our product portfolio into these elements. In other words, we have categorized our portfolio into 4 major segments that basically address these type of requirements. In the OCXO area, we're obviously addressing high stability. We're also addressing low G sensitivity. We're addressing phase noise. And in some of our unique technologies, we're also addressing very low power. CTS has a unique high vacuum technology that allows to go down to 50 milliwatts in some OCXOs. Those are primarily used for very, very high-end applications, but at the same time, those are available in cases where extremely low noise at high frequencies is available. In the next level is the TCXO. So in some applications like 5G mmWave or small cells, there's no need or there's no power to support OCXO, and there's no need for the stability, but yet there's very much of a need for high frequency and low noise. The TCXO could be a very good solution. And in those cases, we offer multiple types of products, whether it's small miniature, 5 by 3.2 millimeter, or bigger type of sizes where additional circuitry and additional noise reduction mechanism is being applied. We can basically cover applications that will go up to millimeter wave frequencies as a reference source. In the next group of components, we have the clock oscillators and the VCXOs, which normally will clock chipsets that primarily used either in fiber optics, wireline type applications as a clock, or in cases where you decide to build your own PLL and you basically discretely put a PLL chip with the VCXO, the loop filter, and others, and basically control your own either noise reduction mechanism or multiplication. And the last but not least, in cases where you really try to integrate, reduce the size, lower the cost, and still maintain very high performance, we came up with integrated solutions, which are, we call them timing modules, but essentially those are frequency synthesizers. And their function is basically integrating, utilizing our own ASIC technology, allowing to reduce the noise of the system in case when you do clock recovery from either Ethernet or you're trying to lock to a GPS and you're trying to get a nice clean signal to basically clock the entire system. Or in cases where you try to multiply, you want to take a 10 megahertz, let's say, multiply it up to a few hundreds of megahertz. These synthesizers will do the job in a very clean way. And I'll show a couple of examples of how it affects the entire system noise as you go to high frequencies. As we move into 5G, our main objective is to increase capacity. And with that, we have to increase modulation rate and modulation bandwidth. We also have to look into the higher carrier frequency that brings along higher sensitivity to noise. So the biggest challenge is how do we create that higher carrier frequency without affecting the system noise and disruption of the data transmitted. So at CTS, we spend a lot of resources and design time into high frequency reference sources that also allow very low noise capabilities. And that is through either reference oscillator like an OCXO or a TCXO, but also in form of a noise reduction synthesizer like a jitter attenuator or a frequency multiplier. When we look at high frequency and increased sensitivity to noise, we're basically evaluating two different domains, and obviously that applies to either wireless system or wireline. In the wireless, we're looking at the frequency domain, phase noise, and EVM. Here, the main contributors are the conversion between A to D and D to A, mismatches between the different blocks, and then the engine of the system, which is the prime reference clock, along with some frequency synthesis through different blocks along the way. The PA and LNA with their internal signal to noise ratio. And then as we go into the front end, you have the antenna and the entire packaging of the data into the higher frequency carrier. When we look at wireline applications, then here we're talking about time domain, and here jitter is the main factor. And the noise contributors here are obviously the analog to digital conversion, again, crosstalk between the different blocks, the main reference clock, along with the matching to either the optical transmitter or the Ethernet transmitter. When we look at noise, there is a direct correlation between the time domain and frequency domain. And here we can see how spurious noise actually translates to the entire form of the signal as it looks on at oscilloscopes. We could see the overshoots and the undershoots at the peaks of the signal, and we could also see some noise at the triggering point, at the rise time and the fall time. So essentially, the best way to characterize the noise is actually in the frequency domain, because there we can actually see the source or the area in the spectrum where the noise applies and how does it actually blend in as it goes into the time domain. That primarily applies to telecommunication systems. Here in this view, you could see a 3D model of a signal source. And when we look at it from the frequency domain, basically what we could see the carrier frequency, and we could see some sort of harmonics, or we could see some spurious noise as it comes out in straight lines on the spectrum analyzer. When we rotate that graph into the time domain, we could see how the blending of the carrier frequency or the center frequency with the harmonics or the non-harmonic signals, which is pretty much the spurious, how do they blend in, and they basically disrupt any digital form of the signal. And so you could see how the correlation between frequency domain and the time domain as it transposed within the system. As we go to design of system with higher carrier frequency and higher modulation bandwidth, we need to understand some of the challenges. Each and every time you will take a local reference clock or outside clock that is running at low frequency and you multiply it up to your carrier frequency, you will be losing 6 dB per decade in the multiplication. So that's just a fact. We also know that when we multiply, we're trying to create harmonics or non-harmonic signals. Those will mix with the carrier frequencies, and as a result, they will also blend in and will bring up the noise floor of the carrier frequency. We also know that as we go to 5G, we go to the millimeter wave, in order to increase the capacity, increase the modulation rate, we will need to run at high frequency, and that will create the challenge for us. And in addition to the signal-to-noise ratio, we are looking at different ways to quantify what would be the contribution of our design, of the components we choose, onto the ultimate result. EVM in wireless systems is used as a methodology for quantifying that level. And obviously, 3GPP quantifies what is the allowed EVM when you look at the wireless system. When you look at wireline systems, we're looking at jitter, system jitter, local clock jitter, transmitters jitter. That is pretty much the noise, but in the time domain. And it's directly proportional to the noise in the frequency domain. In a mathematical way, we use fast Fourier transform to transform the figure from one domain to another. And we will see that in the next upcoming slides, how that is done and what are the contributors. It's important to denote that a reference clock is essentially a frequency reference source. When we look at a frequency reference source, the best way to quantify and qualify the signal coming out of that source is by looking at the phase noise. The phase noise is essentially a single sideband view of that spectrum around the carrier. So essentially, when we look at that plot, there are different regions within the plot that tells us the story of that particular device. When we look at the blue arrow at the left-hand side of this plot, we're pretty much looking at the Q, the quality factor of the resonator that is embedded within the oscillator. Whether it's quartz, whether it's LC, whether it's a ceramic resonator, microstrip, you will see the quality of that resonator by looking at the steepness of that plot. as we go to the middle of the plot, into that middle arrow, we're pretty much looking at the signal-to-noise ratio of the oscillator that drives that particular resonator, whether it's the amplifier, whether it's some filtering, any crosstalks within some of the traces. All that is going to show on that particular area. And when we look at the far end of the plot, we're pretty much looking at regulator noise, any supply voltage that is not filtered properly within the oscillator or being blended within the amplifier, and obviously some varactor noise that is potentially blending as well. For those of you who deal with optical or telecommunication systems, we're basically looking here at an example of an optical transceiver switch that basically can take on one side a gigabit Ethernet at a certain speed, and then it's being switched to multiple subscribers. And all that is done through different line cards. And each of those line cards has its own synthesizer module. But also, in order to have a correlated or synchronous type of switching, we gotta create some level of a clocking that is accurate enough. And all that is coming through either a bits clock or some sort of a high reference GPS signal that is being locked through a local clock, whether it's an OCXO, TCXO, being synthesized and distributed such that the packets are being matched between the input and the output. Now, all that has to be done in a very unique and clean way, and especially as we go to high-speed kind of routers or switches, the cleanliness and the signal-to-noise ratio of those blocks is extremely critical. In this example, pretty much similar to the previous example, we're showing a wireline switch where we have a gigabit Ethernet backplane coming into the node, basically delivers a carrier frequency as well as the data. We have to extract that signal. Through this extraction, the LIU generates some noise, so we're using frequency synthesizers to basically clean the jitter. Also could, in some other cases, multiply it up to a higher frequency and then distribute it to the subscribers in the different line cards. In such cases, the main functionality of the synthesizers is to reduce system noise so that does not disrupt or corrupt some of the data that is being, that could be generated by the node. When we look at jitter, we're pretty much looking at noise within the time domain. And we define it as short-term variations from the ideal position of that particular digital signal within time. So when you look at this example, you're pretty much having the solid red square wave, the ideal case of a 1 unit interval or 1 UI as it will be observed on oscilloscope. The dotted line within the rise and falling edges show the ranges where we could potentially see some fluctuations or some variation that could be translated into jitter as we look at it in oscilloscope. When we look at system jitter noise, we're pretty much looking at the total jitter, which is essentially a sum of the deterministic jitter and the random jitter. On the deterministic side, we're looking at few subcomponents that include crosstalk. We're looking at EMI, and reflection. All those are elements that are measured in the time domain. Crosstalk, we're looking at pretty much leak of energy from one block to the other or through the traces that connect those blocks. When we look at EMI, we're looking at noise that is basically coupled between AC line and RF signal sources. It also could be translated as periodic noise between the data and the clock signals within the system. On the other hand, we're looking at the random jitter, and in the random side, we're looking at frequency domain components. We're looking at short-term noise, we're looking at flicker noise, and thermal noise. All those are elements that are part of what the oscillator, the reference clock that drives the system, will contribute to the overall noise of the system. Now, as we move into wireless system, let's look into the EVM, the error vector magnitude, and the local oscillator noise. So, as we look at the definition, this figure helps us measure the relationship between the modulation accuracy and the transmitter performance, or in fact, the noise. It also helps capturing the error vector between the signal that is transmitted versus the ideal point in the signal constellation. So essentially what we're getting is we're getting a method to evaluate any impairments, any areas where noise affects the quality of our transmitted signal. So with that, we can look at phase noise and frequency errors. We look at imbalances and mismatches that basically create some leakage and unwanted sidebands. We look at compressions and nonlinearities in the signals. As we already seen from the definition of EVM, phase noise is a main contributor to the figure of EVM and consequently the indication about the performance of the transmitter. So as we look at phase noise, we start with the single sideband curve and convert it into RMS phase noise. And we pretty much look into a single figure that is quantified in radians. Essentially, as we look into high bandwidth devices, we need to be at about 10 dB better in the device performance versus the entire system. When it comes to oscillators, it's essentially 50% of what the error vector magnitude in percentage. So 3GPP has defined certain errors that are pretty much correlated to a certain modulation rate. And you can see that from that table in this slide. So just as an example, if most systems today in 4G LTE are running somewhere at 64 QAM, the EVM required from the transmitter is running around 8%. So that means that the oscillator has to be somewhere in the 4% level. Now, when 5G systems are moving up to 256 QAM and even later on to 1024, that EVM figure has to drop down. And for 256, it's already coming down to 3.5%, which is more than a half below what the figure is for 64 QAM. So now that puts a lot of pressure on the local oscillator or the local reference clock with respect to quality and accuracy such that it does not affect the noise level of the entire transmitter. So with that in mind, it's bringing us to the point of conclusion where it's very critical to select the right reference source with its adequate performance to meet the carrier frequency and the modulation rate that we're trying to get out of the base station. Now, to illustrate and give some colors to the definitions that we discussed earlier, we prepared a couple of examples that show differences between different types of reference sources and their impact on the EVM. Our first example starts with a 100 megahertz TCXO that is a real product that was designed by CTS. It utilized a proprietary ASIC-based technology for frequency synthesis. This particular device is also meeting 0.28 ppm over temperature, but the key thing or the key element here is the phase noise. And as you can see from the plot, we're looking at minus 176 dBc on the noise floor. So that would be the first one to look into the impact of the noise level onto the EVM. For the purpose of illustration and calculation, I've used a tool, calculator tool by Jitter Labs. This tool pretty much helps us convert the single sideband phase noise into RMS phase noise, and then calculate the EVM in dB and in RMS. Now, this particular calculation here is showing the EVM at 100 megahertz. So essentially, there was no additional multiplication towards RF as it comes out of the transmitter. So in the case of no multiplication, what we're looking at minus 77, almost minus 177.2 dB, and 0.014 RMS. So pretty low figure as expected since there is no additional multiplication. So if we take that same 100 megahertz oscillator and we multiply the frequency from 100 megahertz to 33 gigahertz, which is a mmWave band, essentially we're introducing a multiplication factor of 330, and that could be translated to a degradation of about 50.4 dBc on the noise floor. So when we look at the EVM degradation of at 100 megahertz, we basically came up from minus 77 dB all the way to minus 34.5. If we look at the percentage of error, we went up from 0.014% RMS to 1.89. So essentially there is an increase, but if you go back to the table that we talked about, the 3GPP table that shows us what's allowed at 256 QAM for 5G systems, essentially the requirements for the entire system is 3.5%. So at 1.89, we are right around the 50% mark, just a little above the 50% mark of the entire system requirement. So if you have taken this particular oscillator as your prime reference clock for the radio, you would still have a good opportunity to meet the EVM of the entire system. Obviously, there will be some degradation due to PA, couplers, antenna matching, and some other losses. But overall, this oscillator would give you a very good starting point. Now, if we move to the second example, we picked a generic TCXO with DPLL, digital PLL multiplication. So the expectations are that the noise floor is higher than the phase noise of the first example. So if before we were running at about minus 176 dBc at the noise floor, now we're talking about minus 143 dBc at the noise floor. Now, the main reason why the noise floor is higher in the second example versus the first example is primarily related to the spurious level of digital PLL. Those use programmable VCOs internal, and that PLL type generates a lot of spurious noise. So obviously the noise floor will go up. So now as we plug in the numbers into our calculator, we could see that at 100 megahertz, again, no multiplication, the EVM is running at minus 57.2 with 0.137%. So essentially on the EVM in dB, we're running somewhere around 20 dB higher than the low noise type of 100 megahertz in the first example. And we're also talking about an order of magnitude higher on the percentage error, 0.137 versus 0.014 originally in the first example. Now, given the results that we got at 100 megahertz for this DPLL TCXO solution, let's multiply the frequency to 33 gigahertz, just as we've done in the previous example, and plug it into our calculator. So with that, we can see that the EVM went up to almost minus 10 dB, and on the percentage error, we're exceeding the 29%. Now, again, if you go back to what 3GPP defined for us, at 256 QAM, we cannot be more than 3.5% for the entire system. And now we can see that just the oscillator is already running at over 29%. So essentially, without even counting the other components in the system, we're already exceeding the spec, and we're not meeting or complying with 3GPP. So this gives you a very good illustration why a proper selection of a prime reference clock and the quality of that prime reference clock is a key for the result of what you'll get at the output of your radio. As we discussed earlier in this session, any network node must be locked into a main network reference, whether it's a GPS, an Ethernet, or an optical transmission line. The clock must be separated and extracted from that reference source. In that process, the reference clock is being contaminated, and a filtering or regeneration of that clock must be introduced. In some cases, designers may use their own PLL solution to clean or regenerate that reference source. At CTS, we designed and introduced a unique technology through an ASIC solution that basically allows, through one single component, to regenerate and distribute that clock in a very clean way to the rest of the system. What we see here in this plot is, as indicated, that red plot shows a very contaminated, very dirty input signal, where the blue plot shows a regenerated, clean, and pristine reference signal that could be distributed into the rest of the circuit. So this example shows a 25 megahertz for this particular case, where we're showing a reference clock that is reaching about minus 135 dBc at the noise floor. And after the cleaning process, we're pretty much gained over 26 dB and getting down to below minus 160 at the noise floor just through that regeneration of the signal. This device is coming in various sizes and various features. We are introducing it in sizes that are reaching 9 by 14 millimeters or 9 by 9.5 millimeters for single and dual-ended outputs. In addition to the clock cleaning function that we need in some cases, we may need also to multiply that reference clock to a higher frequency, like an IF frequency, for example. The key objective here is to do a very clean multiplication such that, one, we do not introduce any disruptive, spurious, or harmonics. At CTS, we developed, as I mentioned, a synthesizer technology through ASIC that allows to do a very clean multiplication. In this case, what we see is a 100 megahertz that was multiplied from a 25 megahertz input source. And as you can see, even at 100 megahertz, we are running at minus 172 dBc at the noise floor. So what it actually means, it means that we took that reference that was contaminated, we cleaned it, and then we multiplied it to 100 megahertz. So essentially, you got a pristine, nice, clean 100 megahertz that you can use for the rest of the functionality within the nodes, the base stations, and so on. The multiplication doesn't have to be an integer type of multiplication. It could be also fractional. Obviously, there are some cases, there is some giveaways when you look at integer versus fractional. But in cases when there is no other choice and you do need to have a fraction multiplication, the capability to do that are available. And one other thing is that this output frequency could come out in various technologies, LVCMOS, LVPECL, LVDS, or in some unique cases, even sine wave is needed. All in all, CTS has introduced a full family of synthesizer solutions. These synthesizer solutions could be used for frequency cleaning, reference frequency cleaning, or for multiplication. They're coming from sizes of 25 by 22 millimeters all the way down to 9 by 9.5 millimeters. with multiple outputs and multiple input versus output frequencies. As you can see, going from 50 to 1 gigahertz in some cases, or 10 megahertz to 200 megahertz. The key element for this module's family is the noise performance. We want to make sure that when we clean the signal, as you have seen in previous examples, whether we're multiplying or we're cleaning, is pristine and is compliant with new standards. And as we go to 5G, and we've seen with the EVM requirements, noise performance is paramount. A new product that we're working on right now has multiple copies at the output, and those could be programmed by the user. So in other words, you specify what is your input reference source and some of the main output frequencies that you may need for your system, and you can program the outputs based on these requirements, whether it's going to be an LVPECL or LVCMOS or LVDS for that matter. All that could be programmed through I2C interface. With that, you could see that, in fact, a whole circuit that in the past was designed discretely through a PLL, IC, a loop filter, phase detector with, in some cases, and the VCXO or some other type of filtering mechanism and a buffer, you can combine it today into one single device that does it all, and it's pretty much a plug and play. As we're getting ready to wrap up this session, I wanted to introduce you to CTS's 5G timing solution family. Whether we're looking at front hole timing, frequency synthesis, or back hole, we're pretty much looking at one single area when it comes to noise, but different functionalities and different stabilities for each of the levels. On the left-hand side, when we look at the front hole, we're looking at TCXO solutions that are pretty much small in size, cost-effective, yet performing in a very, very tight stability type of fashion. From 7x5 to 5x3.2, we can cover, in some cases, -40 to 85, and in some cases even to 105 degrees in those situations where you prefer to eliminate fan cooling. As far as the frequency synthesis or signal cleaning or multiplication, we are looking at the family of different synthesizers. Single-ended input or multiple type, as well as multiple output or single-ended output. All that is done through different sizes, utilizing some of CTS's unique synthesis technology through ASIC that allows us also to go to a small size. We can offer it, like I said, with HCMOS or LVPECL, or in some cases even LVDS and sine wave, all that while keeping the noise paramount for the main feature of these modules. On the backhaul timing, we're looking at high stability, where Stratum 3E is the main driver for compliance. So 11 ppb, peak to peak, from -40 to 85 is the driver, as well as small size and obviously be cost effective. In the next generation of prime reference clocks for systems that are running in millimeter wave, we are seeing a trend where high frequency reference OCXOs and in some cases even TCXOs, to be the drivers for the system clocking. That will eliminate or will minimize the number of multiplication stages that obviously, as we've seen from the EVM examples, will reduce the noise level, the possibility to gain some unwanted modes that will interfere with the output signal and the quality of the signal. In conclusion, we've noted few insights and challenges evolving with 5G systems. Reference sources are becoming more and more critical as we look at higher transmission frequencies and higher modulation rates, given the fact that systems become, at these levels, more sensitive to noise. We can use EVM and phase noise to qualify and quantify the noise level within a system or a specific local reference source. Minimizing the multiplication factor will allow us to keep the signal-to-noise ratio at a low side and eliminate possibility of accumulating any unwanted signals. When multiplying the frequency using any type of synthesizer, it is preferred to use a low bandwidth type of filtering in order to eliminate any sidebands that could be mixing up with the carrier frequency. Last but not least, I wanted to mention that CTS is also working with semiconductor manufacturers, both in the wireline space and the wireless space, as reference sources that could help you as users and designers to quickly design your system with very low noise reference sources. As an example, the Qualcomm FSM 100 small cell 5G mmWave base station has a low noise CTS TCXO embedded as a reference source for that particular device. On the other hand, in the wireline space, we are working with Broadcom in some of their high-speed Ethernet routers with some of our synthesizer solutions to allow a clean input signal into the router such that they can multiply it to high speed. I wanted to thank you once again for participating in CTS's precision timing presentation for 5G systems and all the discussion about noise. We will now take questions.
Thank you, Ronen. Another very interesting presentation. I hope everybody enjoyed that. Very, very detailed. And so let's go straight over to the Q&A. We've got a few questions here for you, Ronen. So first question is there an IEC standard for the measurement of noise for systems?
Yeah, so normally this is a little bit beyond the scope of this presentation, but I can tell you that there's, first of all, to be able to measure noise, you got to compare it to other known sources of signal as being the, let's say, the golden units that will allow to get the error. I found that there's a couple of standards, but the one that I've seen that is more common for a wireless systems is the IEC 61000. 4-3, that was a standard that was used primarily for the 10 megahertz wide LTE type of protocols. And I believe that there's some new standards that 3GPP is coming up with for especially the sub-6 gigahertz, and now as millimeter wave are coming about. So this is something that it's obviously to be searched further, and I'm sure that as more challenges within the deployment is going to come about, they will fine-tune some of those IEC standards.
Okay, thanks, Ronan. Next question. Can you please tell me what type of waveguide is used for a 5G system?
Yeah, so again, that's another question that is more outside the scope of this presentation. But and if you will join my colleague Roger Merrill, he's going to talk a little bit more about the RF side and the filtering. So, but essentially, the waveguides and the whole antenna structure depends on the coverage of the radio. So there's the directional type of antenna, bidirectional types of antenna. Basically, the idea of the selection of technologies minimizing the phase delay. So some slotted technologies are used for the waveguide in order to minimize that and obviously ensure the wideband capabilities. But I guess that this is something that will be more applicable to the next upcoming presentations that will come with the filters, the RF filter discussion.
Yeah, okay, Ronan. And that question came from Anup Chandra. So Anup, and for the rest of the audience, we have two presentations following this one. Coming up at 1:30 Eastern Time, we have what's new in 5G filters for sub-6 gigahertz, and looking at some innovations in universal footprint families. And then at 2:45, if this is useful to you, Roger Merrill, who is Ronan's colleague, is also presenting Riding the Millimeter Wave with High Performance Filters for Full Bands and Narrow Subbands. So those are coming up this afternoon, and they may answer some of your questions. Let's get back to the questions for Ronan. This next question is, what's the impact, if any, Ronan, of a mismatch between a signal source and its respective loads?
So essentially, when we look at a driver and a load, we want to make sure that we have maximum energy absorption. Any energy that is not being absorbed by the load will be reflected back to the source. That kind of reflection can create mismatches. It can create unwanted modes, or what we call sidebands. And as we've seen in some of the slides, when we look at sidebands could be translated into noise, and especially if they fall within the spectrum where we use our transmitter to operate. So essentially, they can disrupt some of the data that is being transmitted. And so it's very critical to select the type of driving power from the source that matches also the entire impedance as being seen by the load plus the transmission line in between, so that we don't have any mismatches that could create some of that disruption.
Okay. Next question, Ronan, comes from Mark Roscoff. Mark asks, do any 5G systems look at peak jitter versus RMS jitter?
Well, so as I described in my jitter discussion, jitter is primarily looking at the time domain, okay? And if you're looking at 5G systems, the unless you're looking at the wireline side, then obviously there is the RMS component versus the peak component, and it's all that is designed and is being calculated such that both the peak and the RMS are kind of they're intercorrelated. When we look at wireless system, as I mentioned, the EVM is the noise definition type of factor, and then we scale it down to the oscillator. So yeah, jitter in peak and RMS are both being factors, but as I said, wireline system and not necessarily the wireless.
Okay. I think we're getting down to the final question, unless any of the audience has more questions for Ronan. We do have time. So if you do have more questions, go ahead and post that via the Q&A button at the bottom of the screen now. And while you're doing that, we're going to address the final question, I think. So, Ronan, this question is, why does a quartz-based synthesizer device offer better frequency multiplication performance than a programmable LC-based device?
Yeah, so so one of the things that I addressed is the fact that quartz has a higher Q than other types of resonance, whether it's LC, whether it's a SAW, whether it's just a digital type of synthesizer. And if we want to get the best signal-to-noise ratio, quartz could give us the best cleanliness and signal-to-noise ratio of the system that will be translated to better noise figure at the transmission end. Now, there's obviously caveats. If you use a quartz, then the programmability and the flexibility is not going to be there. But then as you design the system or the radio, you need to scale down. What's your requirements as far as the noise capability of the radio, and what kind of flexibility can you afford? Because one may not go in line with the other. So our approach is going after the performance. And as 5 millimeter and high-speed modulation rates are coming and becoming more essential, we're seeing the modulation requirements to be dominating the noise level of the system. And for that, quartz could give a much better result than programmable ALC.
Okay. Well, thanks, Ronan, and thanks to everybody for listening in today. I think we've reached the end of the questions. Great presentation. That is the second one in our series today of the virtual summit on 5G, IoT, and cloud, brought to you by CTS. We have two more presentations coming up this afternoon at 1:30 p.m. Eastern. We have Ronan's partner in crime, Mr. Roger Merrill, who is the Director of Technical Marketing and Business Development at CTS. And his first of two presentations this afternoon at 1:30 is titled, let me get the right one here, What's New in 5G Filters for Sub-6 GHz, Innovations in Universal Footprint Families, followed at 2:45 by Riding the Millimeter Wave with High-Performance Filters, Full Bands and Narrow Subbands. So if you have an interest in that, please go over to the CTS website and sign up, or just go to one of the emails that you received from us and you can find a link there. Thank you, Ronan. Ronan, any final comments before we sign off on this one?
No. Once again, thank you for the attendance. Feel free to contact me if there are any other questions following this presentation, and looking forward to work with everybody. Thank you.
Thanks, Ronan. We hope to see you 15 minutes from now. If not, okay. Have a good afternoon.
Thank you. Bye-bye.
Bye.